January the 9th, 1944, Wright Field, Ohio. 3 fighter aircraft sat on the frozen tarmac, their engines silent in the pre-dawn cold. A P-38J Lightning, a P-51B Mustang, a P-47D Thunderbolt. Standard production models, pulled from operational squadrons without modification. Within hours, these machines would demonstrate something the Army Air Force's Materiel command had been told was impossible. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. That aviation fuel could be pushed beyond 100 octane, that American fighters could fly faster, climb higher, and hit harder than anyone believed possible. The fuel waiting in steel drums nearby wasn't supposed to exist. Every petroleum engineer in America had said the chemistry wouldn't work at scale. Every oil company executive had calculated the economics and declared it unfeasible. Yet, here it sat, rated at 110/150 octane, the product of a chain of seemingly impossible achievements stretching back 2 decades. This is the story of how a French tank officer's obsession with race cars, an American stunt pilot's engineering doctorate, and the desperate mathematics of war transformed not just the P-47 Thunderbolt, but the entire Allied air campaign. It's a story about the invisible advantage, the one that German pilots never saw coming because it flowed through fuel lines rather than showed up on blueprints. And it begins not in an aircraft factory or a military laboratory, but in the oil refineries of Marcus Hook, Pennsylvania, where a process considered commercially impossible was producing 40,000 barrels per day of fuel that would help decide who controlled the skies over Europe. The mathematics of air combat in 1944 were brutally simple. Speed meant survival. Altitude meant advantage. Rate of climb meant intercepting bombers before they reached their targets. Every additional mile per hour, every extra 1,000 feet of ceiling, every faster minute to altitude translated directly into tactical superiority. And all of it, every measure of performance, traced back to a single variable that pilots never saw but felt in every engagement. Manifold pressure. The measure of how much air and fuel an engine could compress into its cylinders before ignition. At sea level, a normally aspirated engine, one without supercharging, operated at 29.92 inches of manifold pressure. The Pratt & Whitney R2800 double wasp engine powering the P-47 Thunderbolt, with its turbo supercharger system, could safely operate at 65 inches of manifold pressure in 1943, more than twice atmospheric pressure. But there was a hard limit. Push the manifold pressure higher, and the fuel would detonate prematurely. The technical term was knock. The practical result was destroyed pistons, cracked cylinder heads, catastrophic engine failure. The limit wasn't the engine's mechanical strength. American metallurgy could build engines to withstand far higher pressures. The limit was the fuel itself. Its tendency to explode under compression before the spark plug fired. This invisible ceiling had constrained aircraft engine development since the invention of the internal combustion engine. Higher compression ratios produced more power, but only if the fuel could withstand the compression without detonating. It was a chicken and egg problem that had trapped the aviation industry for decades. Engine manufacturers wouldn't invest millions developing higher performance engines when no fuel existed to run them. Oil companies wouldn't invest in refineries for high-octane fuel when no engines existed that required it. By 1938, American military aviation was running on the same grade of fuel as automobiles, 87 octane, adequate for the low-compression engines of the era, completely inadequate for what was coming. The measure of this inadequacy became visible in the skies over France in May 1940. Royal Air, Force Hurricanes and Spitfires, filled with 81/87 octane fuel, engaged German Bf 109 seconds running on 91/100 octane. The Luftwaffe fighters were 20 to 30 miles per hour faster. They climbed higher. They could choose when to engage and when to disengage. British pilots, even in machines that could outturn the German fighters, found themselves at a systematic disadvantage. The difference wasn't airframe design. It wasn't pilot skill. It was the fuel in their tanks. The Germans understood what the British were only beginning to learn, that modern air combat would be decided as much in oil refineries as in aircraft factories. But the seeds of Allied fuel supremacy had been planted years earlier, in two places that seemed to have nothing to do with military aviation. In a French mechanical engineering workshop, where a tank officer had become obsessed with automobile racing, and in the research laboratories of an American oil company, where a test pilot with a doctorate was asking questions that made accountants nervous. Eugene Jules Houdry was born near Paris on April 18, 1892, into a family that built structural steel. He graduated first in his class from the École des Arts et Métiers in 1911, earning a gold medal from the French government. He also captained his school's football team to the national championship in 1910. A brilliant engineer and accomplished athlete, he seemed destined for a conventional career in the family steel business. Then came the Great War. Houdry served as a lieutenant in the tank corps of the French army, earning the Croix de Guerre for bravery. The experience of mechanical warfare, of machines grinding through mud and metal, left him with an engineer's appreciation for what power and fuel could accomplish together. After the armistice, he returned to civilian life with a new passion: automobile racing. France, in the early 1920s, faced a problem that seemed distant from racetracks and speed records. The nation produced almost no petroleum. Every gallon of gasoline had to be imported at crushing expense. France possessed vast deposits of lignite and coal, but no economical way to convert them into usable motor fuel. In 1922, Houdry traveled to the United States. He watched the Indianapolis 500. He toured the Ford Motor Company plant in Detroit. He saw an industrial future powered by internal combustion engines, and he understood that France couldn't participate without solving its fuel problem. The French government, recognizing the strategic implications, asked Houdry to develop a method to produce gasoline from France's abundant coal and lignite deposits. Houdry threw himself into the problem with characteristic intensity. He experimented with a process called cracking, heating coal to extreme temperatures, to break down large, complex hydrocarbon molecules into smaller ones, suitable for gasoline. By 1925, he had developed a working method. It produced gasoline from coal, but the economics were impossible. The process consumed too much energy, produced too much waste, and cost far more than importing petroleum-based fuel. Most engineers would have abandoned the project. Houdry had proven the concept wasn't commercially viable, but he had observed something that captured his attention completely. The gasoline produced through cracking had a higher octane rating than anything available from conventional petroleum refining. It burned more cleanly, it resisted knocking, it enabled higher engine compression. In 1927, Houdry made the discovery that would eventually change warfare. He found that introducing a catalyst, specifically naturally occurring aluminosilicates, into the cracking process dramatically improved efficiency. The catalyst didn't just speed up the reaction, it guided it, selectively breaking down only the large molecules while leaving smaller ones intact. Even better, the catalyst could be regenerated, heated in an oxygen-rich environment to burn off accumulated carbon, then reused indefinitely. For the first time, catalytic cracking of petroleum into high-octane gasoline became theoretically possible at commercial scale. Theoretically possible and actually possible were different problems. Houdry needed industrial partners with refineries, capital, and petroleum expertise. In 1930, after the Socony Vacuum Oil Company and Sun Oil offered financing, he moved to the United States and established the Houdry Process Corporation. The timing was catastrophic. The Great Depression had begun. Oil companies were hemorrhaging money. Nobody wanted to invest millions in experimental refining technology for a product with no market. Houdry's catalytic cracking process, brilliant in theory, sat dormant while the economy collapsed. The breakthrough needed an advocate who understood both the engineering and the strategic implications. Someone with the technical expertise to evaluate the process and the celebrity to get people to listen. In 1930, Major James Harold Doolittle left active duty in the United States Army Air Corps and joined Shell Oil Company as aviation manager. He retained his reserve commission, but his immediate concern was civilian. Doolittle was uniquely qualified for what would become his most important contribution to Allied victory. He held a doctorate in aeronautical engineering from MIT, one of the first such degrees ever awarded. He was also one of America's most famous pilots. In 1922, he had made the first coast-to-coast flight in under 24 hours. In 1929, he had made the first complete instrument flight, taking off, flying, and landing without any outside visual reference. In 1931, he won the Bendix Trophy race. In 1932, he set a world speed record of 296 miles per hour and won the Thompson Trophy race flying the notoriously unstable GBR-1. Doolittle understood something that almost nobody else in America had grasped, that a crisis was approaching. He had seen the chicken and egg problem firsthand. Engine manufacturers wouldn't develop high-compression engines without high-octane fuel. Oil companies wouldn't invest in high-octane fuel production without engines that needed it. Meanwhile, in Germany, the Luftwaffe was flying fighters with fuel-injected Daimler and BMW engines, burning fuel with octane ratings American aviation couldn't match. Doolittle had toured German aircraft factories. He had watched their fighters fly. He understood what was coming. In the midst of the Depression, with the military budget slashed and isolationism ascendant, Doolittle began lobbying for something that made no immediate economic sense. He wanted the United States Army Air Corps to adopt 100-octane fuel as its standard. The resistance was predictable and overwhelming. 100-octane fuel cost $25 per gallon to produce in laboratory quantities. Automotive and aviation fuel cost less than 20 cents per gallon. The military saw no reason to multiply its fuel costs by more than 100 for a performance improvement in engines that didn't yet exist. Doolittle persisted. He used his celebrity to gain access to decision-makers. He used his engineering doctorate to explain the technical advantages. He used his racing victories to demonstrate what high-performance fuel could achieve. He pointed to Germany's obvious preparations for war. He made the case that American aviation was being strangled by its own logistics, that the desire to use one standard fuel grade for aircraft, vehicles, and equipment was preventing the development of air superiority. By 1934, Shell Oil had begun small-scale production of 100-octane fuel using hydrogenation and tetraethyl lead additives. The cost dropped from $25 per gallon to about $2 per gallon. Still 10 times more expensive than standard fuel, but no longer completely prohibitive. Doolittle used this fuel to set aviation speed records and win air races, providing visible proof of its value. Still, the military hesitated. $2 per gallon was $2 per gallon. In 1934, Congress had cut the military budget to its lowest point since before World War I. The Army Air Corps was flying obsolete biplanes. Spending money on expensive fuel for high-performance engines that didn't exist seemed like a fantasy. Then, in 1933, Adolf Hitler became Chancellor of Germany. In 1935, Germany openly repudiated the Versailles Treaty and began massive rearmament. In 1936, German forces reoccupied the Rhineland. The likelihood of another European war shifted from possible to probable. The question was no longer whether the United States needed high-octane fuel, but whether it could produce it economically before war arrived. That's where Eugene Houdry's impossible process re-entered the picture. His catalytic cracking method could produce high-octane gasoline, but nobody had proven it could work at industrial scale with economics that made sense. In 1936, the Houdry Process Corporation opened a pilot plant in Paulsboro, New Jersey, operated by Saucony Vacuum Oil. The plant produced 2,000 barrels per day of high-octane gasoline, not laboratory quantities, not experimental batches. 2,000 barrels per day of commercially viable fuel. In 1937, Sun Oil opened the first full-scale Houdry unit at its Marcus Hook refinery in Pennsylvania. The plant produced high-octane fuel for Sun's premium New Blue Sunoco brand. The fuel worked, the process worked. The economics, while not perfect, were close enough to viability that oil companies began paying attention. That same year, 1937, Germany began negotiations to acquire licenses for the Houdry process. Eugene Houdry, who had fought German tanks in the Great War, watched Nazi intentions with growing alarm. He broke off negotiations in 1937, refusing to provide the technology to a regime preparing for another war. His decision would have consequences he couldn't predict. The Germans would enter World War II with good aviation fuel, but not great aviation fuel. Their catalytic cracking technology would never match Allied capabilities. By 1938, Shell Oil and Standard Oil of New Jersey had won contracts to supply test quantities of 100-octane fuel to the Army Air Corps. The price had dropped to 17.5 cents per gallon, only 2.5 cents more than 87-octane fuel. Doolittle's years of lobbying had created a market. Houdry's process had made production economically viable. In 1938, the Army Air Corps and the Navy agreed to standardize on 100-octane fuel for combat aircraft. Suddenly, the chicken and egg problem was solved. Oil companies had a guaranteed military market. Engine manufacturers could design high-compression engines knowing fuel would be available. Aircraft designers could plan for power plants that previous fuel limitations had made impossible. The transformation of American military aviation began immediately. The Pratt & Whitney R2800 Double Wasp, the engine that would power the P-47 Thunderbolt, was designed from the beginning to exploit 100-octane fuel's properties. Its 18 cylinders, arranged in 2 rows, could develop 2,000 horsepower at sea level. With the turbo supercharger system, it could maintain high power output to altitudes above 30,000 feet. The engine's compression ratio and manifold pressure settings assumed 100-octane fuel. Without it, the R2800 couldn't exist. Without the R2800, the P-47 couldn't exist. The invisible advantage was being built into American air power from the ground up, but 100-octane fuel, revolutionary as it was in 1938, represented only the beginning. The octane rating system measured resistance to knocking under lean mixture conditions. The second number in aviation fuel ratings, the performance number, measured power output under rich mixture conditions with maximum fuel flow. 100-130-octane fuel, which became the Allied standard by 1940, could produce 30% more power than 91-100-octane fuel under rich mixture conditions. That difference, 30% more power, translated directly into combat advantage. In May 1940, as German fighters swept across France, the Royal Air Force began receiving American 100-octane fuel. Rolls-Royce Merlin engines in Spitfires and Hurricanes were modified in strengthened cylinder heads to handle 12-pound boost pressure instead of 6.25-pound boost. The modification was approved in March 1940. By July, when the Battle of Britain began, RAF fighters were burning American 100-octane fuel. Luftwaffe pilots, who had dominated the skies over France just weeks earlier, discovered they were now fighting different aircraft, not different airframes. The Hurricanes and Spitfires were the same machines, but filled with 100-octane fuel and cleared to use full boost pressure, they were 20 to 30 miles per hour faster. They could climb higher, they could sustain combat power longer. The fuel difference, invisible to observers, had shifted the aerial balance. British historians would later estimate that the octane advantage, just 13 points, provided the margin of victory in the Battle of Britain. 13 points of octane rating translated into enough performance advantage that Luftwaffe fighters couldn't systematically dominate RAF defenders. The British could choose when to engage. They could climb to altitude before German bombers arrived. They could disengage when outnumbered. The air battle that was supposed to clear the way for German invasion instead ground into a war of attrition that Germany couldn't win. All because of fuel chemistry that German refineries couldn't duplicate. By 1941, when the United States entered the war, American production of 100-octane aviation fuel had reached 40,000 barrels per day. Almost all of it came from Houdry catalytic cracking units. 14 Houdry plants operated across the United States, producing 90% of all catalytically cracked aviation fuel. The scale-up from 2,000 barrels per day in 1936 to 40,000 barrels per day in 1941 represented one of the great industrial achievements of the war's early years. Eugene Houdry, working with obsessive combat intensity, had personally supervised much of the expansion. He often worked for days without sleep, pushing his teams to solve each technical problem as it emerged. His colleagues called him Mr. Catalysis. Continuing Part 2, Final Section. His approach to research resembled Thomas Edison's. He conducted thousands of experiments, relying on intuition and experience rather than theoretical chemistry. One associate later said, "Houdry had one remarkable characteristic, and it was not inventiveness, it was the courage to make a total commitment to his convictions." If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. That courage, that absolute commitment, had created an industrial process that was now fueling Allied air superiority. But the military wasn't satisfied. 100-130 octane fuel had transformed air combat, yet the Army Air Force's Materiel Command believed performance could be pushed further. The question was whether the chemistry would cooperate, whether catalytic cracking could produce fuel with even higher anti-knock properties, whether the economics could ever make sense. By 1943, as American bomber formations began striking deep into German territory, the need for every possible performance advantage had become undeniable. American fighters needed to escort bombers to targets hundreds of miles inside enemy territory. They needed to fight through German interceptors. They needed to maintain high power output at extreme altitudes, where bomber formations cruised. Every additional mile per hour of speed, every extra 1,000 feet of operational ceiling, every faster rate of climb meant more bombers returning home. The Materiel Command initiated a crash program to develop fuel beyond 100 octane. The chemistry was brutally difficult. Pure iso-octane, the reference fuel defining 100 octane, represented the upper limit of the original rating system. Fuels exceeding 100 octane received performance numbers instead of octane. Ratings, comparing their power output to pure iso-octane. A fuel rated 110-150 meant it performed 10% better than iso-octane under lean mixture, 50% better under rich mixture. Creating such fuel required pushing catalytic cracking to its theoretical limits and adding expensive blending components. By late 1943, experimental batches of 110-150 fuel existed in laboratory quantities. The Materiel Command needed to know whether it would actually improve combat aircraft performance, whether the chemistry translated into tactical advantage. In January 1944, they assembled 3 aircraft at Wright Field for testing: a Lockheed P-38J Lightning, a North American P-51B Mustang, a Republic P-47D Thunderbolt. The aircraft were relatively early production models, pulled from operational units without modification. Standard combat fighters, not specially prepared test aircraft. The fuel was poured into their tanks, the engines were started, and American aviation crossed another invisible threshold. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The P-38J, powered by 2 Allison V171089 engines, was cleared to use 75 inches of manifold pressure with the new fuel. Previously, it had been limited to 60 inches. The performance improvement was immediate and dramatic. Speed increased across the entire altitude range. Rate of climb jumped by hundreds of feet per minute. The P-51B, with its Allison V16507 engine, also received clearance for 75 inches of manifold pressure. Similar performance gains. But the P-47D presented a different situation. The Army Air Force kept its R2-80063 radial engine at 65 inches maximum manifold pressure, the same limit as with 100/130 fuel. The decision reflected conservative engineering. The R2800's air-cooled design meant cylinder head temperatures were already high. Pushing manifold pressure higher risked overheating even with better fuel. Yet even at the same manifold pressure, the P-47D showed measurable improvement. The higher octane fuel burned more efficiently. It produced more power per unit of fuel consumed. On average, the P-47D was 19 miles per hour faster from sea level to 35,000 feet. Its rate of climb increased by 410 feet per minute. Those numbers, 19 miles per hour and 410 feet per minute, might seem modest. They weren't. In air combat, 19 miles per hour meant the difference between catching an enemy fighter and watching it escape. 410 feet per minute better climb rate meant reaching bomber formations before German interceptors did. The cumulative tactical advantage was enormous. The test results convinced the Army Air Forces to adopt 110/150 fuel immediately. Not after further testing, not after production infrastructure was built. Immediately, by mid-1944, the new fuel was flowing to combat units in Europe and the Pacific. Production climbed from 40,000 barrels per day in 1941 to 200,000 barrels per day in 1943. By 1944, Houdry plants alone were producing 373,000 barrels per day. The scale of this achievement is difficult to overstate. American industry had taken a laboratory curiosity in 1936 and scaled it to nearly 400,000 barrels per day in 8 years, all while fighting a global war. The impact on P-47 operations was immediate and measurable. The Thunderbolt, already respected for its rugged durability and devastating firepower, became faster and more lethal. Pilots reported they could now catch German TFW-190 fighters that previously could outrun them in level flight. They could maintain formation with bomber streams at higher altitudes. They could climb faster to intercept German jets, the Me-262 seconds that appeared in late 1944 and represented Nazi Germany's last technological surprise. The 56th Fighter Group, the only 8th Air Force unit that flew P-47 seconds throughout the entire war by choice rather than necessity, demonstrated what the improved fuel meant in practical terms. They claimed 677.5 air victories and 311 ground kills at the cost of 128 aircraft. Lieutenant Colonel Francis Gabreski scored 28 victories. Captain Robert Johnson scored 27. Colonel Hubert Zemke scored 17 3/4. The 56th remained the 8th Air Force's top-scoring group in aerial victories throughout the war. Those victories weren't just about pilot skill or aircraft design. They were about the cumulative advantage of 19 additional miles per hour, 410 extra feet per minute climb rate, sustained high power output at extreme altitude, advantages that came from fuel chemistry invisible to everyone except the petroleum engineers who created it and the pilots who felt it in combat. The Germans, despite their advanced chemical industry, never caught up. Their best aviation fuel rated approximately 90 to 95 octane by American standards, though German rating systems used different measurements that made direct comparison difficult. The Third Reich produced synthetic fuels from coal using the Fischer-Tropsch process, but these fuels couldn't match catalytically cracked petroleum for octane rating. German pilots in FAR 190 seconds and BF 109 seconds, flying aircraft that were aerodynamically competitive with American fighters, found themselves systematically disadvantaged by what flowed through their fuel lines. The title's claim about 490 miles per hour requires historical precision. Standard production P-47D Thunderbolts with 110/150 fuel achieved approximately 426 miles per hour at 30,000 feet. The 19 miles per hour improvement from better fuel brought operational speeds to roughly 445 miles per hour under optimal conditions. 490 miles per hour was achieved by experimental variants with completely different engine configurations. The XP-47H, fitted with a Chrysler 40-2220 inverted V liquid-cooled engine, was expected to reach 490 miles per hour, though sources disagree on whether it actually met that target. The XP-47J, with an extensively modified R2800 engine and contra-rotating propellers, achieved 504 miles per hour in August 1944, becoming the first piston engine fighter to exceed 500 miles per hour. But the XP-47J's speed came from radical engine modifications, not fuel, alone. The honest accounting is this: 110/150 fuel made standard P-47Ds 19 miles per hour faster. It increased their climb rate by 410 feet per minute. It extended their high-altitude performance envelope. Those improvements, multiplied across thousands of aircraft and tens of thousands of combat sorties, contributed materially to Allied air superiority. The fuel didn't turn P-47 seconds into 490 monsters through chemistry alone, but it gave American fighters a systematic advantage that German aviation couldn't counter. An advantage built in oil refineries, invisible in combat, decisive in aggregate. By the war's conclusion, the United States had produced almost 90% of all 100-octane and higher aviation fuel used by Allied forces. American refineries were producing more than 20 billion gallons of high-octane fuel annually. The Houdry process and subsequent improvements in catalytic cracking had made this production possible. Without it, American industry would have been limited to thermal cracking, which produced lower octane fuel in smaller quantities. Without high-octane fuel, American aircraft engines would have been limited to lower compression ratios and reduced power output. Without that power, American fighters would have been slower, climbed less effectively, and operated at lower altitudes. The entire structure of American air superiority rested on a foundation of invisible chemistry. Eugene Houdry watched the war effort from his laboratories in Linwood, Pennsylvania, which had become the research and development center for catalytic processes. In 1942, he became an American citizen. He also helped organize and later led the committee France Forever, which supported the Free French forces fighting to liberate his homeland. After France fell to Germany in June 1940, Houdry had offered to return and advise the French government on fuel production. The Germans had captured French petroleum infrastructure before he could implement improvements. Now, American fuel produced by his process was powering the aircraft that would eventually liberate France. The irony wasn't lost on him. The tank officer who had fought Germans in the Great War was helping defeat them again through chemistry rather than combat. Jimmy Doolittle, who had lobbied for 100-octane fuel adoption in the 1930s, spent the war demonstrating that air power required more than good fuel. In April 1942, he led the famous raid on Tokyo, launching B-25 bombers from the carrier Hornet in a mission everyone said was impossible. He later commanded the 8th Air Force in Europe, overseeing the strategic bombing campaign against Germany. But historians have argued that his contribution to fuel development mattered more than his wartime flying. Walter Boyne, former director of the National Air and Space Museum, wrote that Doolittle did more and for the Allied effort in World War II as a scientist than as an airman because of his push for the development of 100-octane fuel. The assessment is debatable. Doolittle's wartime leadership was certainly consequential, but Boyne's point stands. Without the fuel infrastructure Doolittle helped create, the aircraft he commanded would have been less capable, less effective, possibly inadequate for their missions. The P-47 Thunderbolt ended the war with an aerial kill ratio of 4.6 to 1 across more than 746,000 sorties. It served in every theater, from Europe to the Pacific to the Mediterranean. Pilots loved it for different reasons than they loved the P-51 Mustang. The Mustang was elegant, long-ranged, beautiful. The P-47 was brutal, survivable, unstoppable. Its radial engine could absorb punishment that would destroy liquid-cooled engines. Its .850 caliber machine guns could obliterate ground targets. Its ability to carry bombs, and rockets made it arguably the war's most effective fighter bomber. From D-Day to VE Day, P-47 pilots claimed to have destroyed 86,000 railroad cars, 9,000 locomotives, 6,000 armored vehicles, and 68,000 trucks. The ground attack effectiveness came partly from the aircraft's rugged design, but it also came from the fuel that let it carry heavy loads to altitude, maintain high power during attack runs, and bring damaged aircraft home. After the war, Eugene Houdry turned his attention to a new problem: automobile exhaust and air pollution. In 1950, when early studies of Los Angeles smog were published, Houdry became concerned about the role of gasoline engines in air quality. He founded Oxy-Catalyst Company to develop catalytic converters for automobiles. The technology was decades ahead of its time. Catalytic converters couldn't work while gasoline still contained tetraethyl lead, the octane-boosting additive Thomas Midgley had. Developed in 1921, lead poisoned the catalyst, rendering it useless. Not until the 1970s, when lead was banned from gasoline and the Clean Air Act mandated emission controls, did catalytic converters become standard equipment. Houdry had received a patent for his automotive catalytic converter design in 1956, but he didn't live to see it implemented widely. He died in July 1962, at age 70, having transformed petroleum refining and laid the groundwork for emission control technology. His legacy in military aviation alone would have been sufficient for historical significance. The Houdry process produced 90% of catalytically cracked aviation fuel during the first 2 years of American involvement in World War II. That fuel powered the fighters that won air superiority over Europe and the Pacific. It enabled the bomber campaigns that destroyed German industrial capacity. It gave Allied aircraft systematic performance advantages that German aviation couldn't overcome. The American Chemical Society designated the Marcus Hook refinery site, where the first full-scale Houdry unit operated, as a National Historic Chemical Landmark. The designation recognized not just the technical achievement, but the strategic impact. Modern warfare had been decided in part in that refinery. The men who flew P-47 Thunderbolts never met Eugene Houdry. They never visited his laboratories. Most had no idea how catalytic cracking worked or what 110/150 fuel meant chemically. They experienced the results directly, the engine power that pressed them into their seats during takeoff, the sustained high performance at altitude, the 19 extra miles per hour that let them catch enemy fighters, the 410 additional feet per minute that let them reach bombers before interceptors did. They felt the advantage without knowing its source. That invisible advantage, built in refineries and delivered through fuel trucks, represented something profound about industrial warfare. Victory didn't just come from superior weapons or better tactics. It came from the accumulation of small systematic advantages across every dimension of military power. Better fuel meant better engine performance. Better engines meant better aircraft. Better aircraft meant air superiority. Air superiority meant successful bomber campaigns. Successful bomber campaigns meant grinding down enemy industrial capacity. The chain of causation stretched from petroleum chemistry to strategic victory, with each link essential. The story of how fuel transformed the P-47 is ultimately a story about people who solved problems everyone said couldn't be solved. Eugene Houdry, told that catalytic cracking wasn't commercially viable, built an industry around it. Jimmy Doolittle, told that 100-octane fuel was too expensive, lobbied until it became standard. Petroleum engineers, told that 110/150 fuel couldn't be produced at scale, created refineries producing hundreds of thousands of barrels daily. Test pilots at Wright Field, handed experimental fuel and told to see what it could do, discovered that American fighters could be faster, climb better, and fight more effectively than anyone had calculated. Each achievement built on previous ones, creating capabilities that seemed impossible before they became routine. The P-47 Thunderbolt flew its last combat mission in the Pacific Theater in August 1945. Production ended in October 1945, with the last aircraft rolling off the assembly line just as the war concluded. More than 15,000 Thunderbolts had been manufactured. They had flown hundreds of thousands of sorties. They had helped establish air superiority that made Allied victory possible, and running through every mission, powering every sortie, flowing invisibly through fuel lines and combustion chambers, was the fuel that Eugene Houdry had made possible through a process everyone said wouldn't work. The fuel that Jimmy Doolittle had fought for when everyone said it was too expensive. The fuel that gave American aviation a systematic advantage German industry couldn't overcome. The mathematics were simple in retrospect. 19 miles per hour faster, 410 feet per minute better climb, sustained high power at extreme altitude. Those numbers, multiplied across thousands of aircraft and hundreds of thousands of sorties, accumulated into air superiority, and air superiority, invisible as fuel chemistry, made the difference between victory and defeat. The P-47 never hit 490 miles per hour through fuel chemistry alone, but the fuel made it fast enough, powerful enough, and capable enough to help win the war. Sometimes, that's all that matters. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.